Hello and welcome back. In this part of the class, we will be discussing a little bit of the definitions. See, it is a very important thing to be able to understand exactly what the definitions of some of these concepts are. These definitions are pervasive. They will exist in perpetuity throughout this class, and we will be using them extensively. So, very important that you understand the definitions that we're going to be covering today. Right? So, to start, we're going to talk about the most fundamental aspects of electronics, and that is voltage and current. Okay? Both of these are very important concepts. Now, the thing about voltage and current is most people know this formula. Okay? I just use the word most people like that's actually true. It's not. Most people come into this class knowing Ohm's Law. Okay? In Ohm's Law, you know V equals IR. What does that mean? Well, I'll tell you what it means. It means voltage is equal to current times resistance, which is great when you are studying a resistive circuit. Okay? It is not great when you are studying an inductance circuit or a capacitance circuit. This relationship is not always true. However, there is always a relationship between voltage and current in a component. It's just not always this one. So when I ask the question, what is voltage? Usually I get a lot of blank stares because it's one of those like, what? I don't know. It's a volt. Voltage is a fundamental unit of power. Okay? With voltage, what a lot of what voltage is it's like, I like to describe voltage as it's like, imagine a mountain. Okay? Imagine having a mountain. And you're standing on top of this mountain, chilling out with your bros, and you want to decide to throw a ping pong ball down this mountain. Okay? If you throw the ping pong ball and you're throwing it down the mountain, the ping pong ball is going to travel down the mountain. Okay? That's a lot harder when you're standing at the foot of a mountain. And you're just like, hey, I'm going to throw a ping pong ball, and it's going to go up the mountain. It doesn't work like that. It's whoop. And the reason for that is because everything goes from a state of higher energy to lower energy. Here, your tennis ball or your ping pong ball or whatever falls down the mountain because it goes from a state of high energy to a state of low energy. Okay, that's basic physics right there. High energy to low energy. And that's the natural progression of how this works. High energy to low energy. You cannot take an object at low energy and throw it at a wall and then have it suddenly just be like, whoop, all the way up that mountain. High energy. It doesn't work like that. Okay? High energy to low energy. Voltage is, well, the definition of voltage, it is the amount of energy per electron. Okay? That's the definition of voltage. Okay, so what voltage is? It's the amount of energy that a single electron has. Sometimes it's called electron volts. It's whatever. But the idea is, it's how much energy it has. Here, if we're using the mountain analogy, how high up on that mountain are you? If you're over here, and you're like, I'm throwing a ping pong ball down this mountain, and you totally throw a ping pong ball down the mountain, it's not going to fall very far. It doesn't have a whole lot of energy. It doesn't start with a whole lot of energy. You start way up here, you have a lot more energy. Okay? Start way down here, you have no energy at all. Okay? Now, just like a mountain, all of this is relative. Because, you know, if this is flat ground, this is the valley in between the mountains, yeah, okay, you may not have any energy, but let's say that the mole people decide to dig a hole that goes way down here. Now all of a sudden you have a ton of energy. You throw that ping pong ball and it's, dink. Okay, lots of energy there, or hopefully not you falling into the hole. Mole people can be rather rude. So, when it comes down to it, this is a relative measurement just like height, but it comes down to how much energy is contained per electron, okay? The more energy, the more ability it has to do stuff. Energy itself is fundamentally related to work. Work is the ability to change energy, or you could state that energy is the ability to perform work. So those kinds of things. We're going to be talking a little bit more about energy and power in the next lecture. This lecture, I kind of want to focus on voltage and current. Okay? So this idea of voltage is the amount of energy that an electron has. And I'm using a mountain analogy because you're throwing it down a mountain. If you jump on a ski lift or you throw this on some kind of a ski lift, this is going to increase the energy of that ping pong ball. Okay? You have a whole lot of ping pong balls, throw it on a ski lift, great. You have a whole lot of energy being transferred to those ping pong balls. It's increasing the energy, and that's the way that system works. Okay? Increasing the energy of an electron takes an active process. That energy has to come from somewhere. You can't just be like, I'm throwing a ping pong ball at a mountain, ping pong ball just decides, boop, boop, top of the mountain. And then all of a sudden becomes Swedish or something. Ah, dang, I should have used my Swedish accent in the beginning of this. Regrets. I have regrets. I'll get over it. Hello, family. 8 o'clock in the morning is not good for my mentality. This is where it brings out my psycho. You're going to get to see that in person. That's ridiculous. Anyways, so when it comes to energy, okay, the more energy it has relative to some baseline level, the more energy it has. Okay, if you're standing on a mountain and the mountain's at 14,000 feet and you're standing above a plateau that's at 13,995 feet, you have a 5-foot drop, and you sit there and you're like, I'm gonna throw this ping pong ball to 14,000 feet, it's got so much energy! It takes energy for days! You throw it out here, it's gonna fall 5 feet. Okay? The energy difference is not huge. And that's kind of this thing. The speed of the ping pong ball when it hits the ground is not gonna be that high, or I guess tennis ball would have been a better analogy here. Throw a tennis ball out of here, speed as it hits the ground is going to be pretty low. Why? Because it doesn't have a whole lot of energy. There's not a whole lot of energy difference. Now, if you're standing at a 14,000 foot mountain and you decide to throw it off all 14,000 feet of it, it's going to have a heck ton of energy by the time it hits the ground. This is a massive energy jump. So it doesn't matter that you're at 14. It matters what it's relative to. Okay? Voltage is relative between 2 points. Just like height is relative between 2 points. Okay? The amount of energy per electron is relative between 2 points. There's no absolute, well, I guess there is, but nobody measures relative to the absolute zero level of electric voltage. Okay, you look at the 120 volts that surges through a 120 volt outlet. It's 120 volts relative to itself. That's it. It's not relative to any other thing. Sometimes when you touch an outlet, you get shocked. Why? Because that 120 volts relative to something is actually relative, it's 135 volts relative to ground at some points. Okay? Everything is relative here, and that relativity changes. And that does make electrical circuits a little bit harder to analyze. Okay? And we're going to get into a lot more detail on this later in the semester. But what you need to know about voltage is energy per electron. Can't say that enough. All right. So voltage is the energy per electron, much like throwing a ball off of a mountain. More energy means it's got more energy. What current is current is the amount of electrons traveling per time unit, usually per second. An ampere is a coulomb per second. Okay. So if we're trying to figure out current, the analogy is if I have a mountain and I throw my tennis ball off, that tennis ball is going to pick up speed. The more energy it starts with, the higher the speed at the bottom. Okay? Now, that's not quite what current is. Current isn't speed. The speed of current actually stays the same. Electron speed, they travel around the speed of light, which is one of the reasons why electrical circuits are so unique in physics, is because electrons travel near the speed of light. But what we can say is, if I were to throw a basket of tennis balls off of this mountain, all of those tennis balls have a lot of energy, because amount of energy per tennis ball. And we would have, maybe there's some bushes on the way down, or some trees that are sticking out of the mountain, or maybe there's some guy down here that's dressed in a leprechaun suit. Maybe there's okay, I don't actually remember what a leprechaun hat looks like. So it's some dude. Okay, the amount of tennis balls you throw down, it's going to have some resistance. The more tennis balls you have, though, the more tennis balls are going to reach the bottom. And you throw them at a higher energy level, well, you're more likely to get more of them to reach the bottom, despite however many obstacles they have to go through to get there. Okay, what current is it's the amount of electrons traveling at a certain speed. I like to, in this analogy, liken it to the speed of an object. Higher energy means higher speed, but in particle physics, really what it is more energy means more particles that are traveling. Okay. In current, if you only have one electron over here, and that electron just travels this direction and ends up over here, you have a very low current. Doesn't matter how fast this is. Traveling at the speed of light doesn't matter. One electron traveling over here, low current. You have a lot of electrons traveling over here, you have a pretty high current. Okay? We can, instead of using a tennis ball, we can instead say, this is not a tennis ball, it's a bucket of water. Wow, that doesn't look like a bucket of water. Let's try this again. It's a bucket of water. There we go. I'm going to dump this bucket of water down this mountain. Okay? Now, if I dump a bucket of water and it has to go 5 feet, travel through a tree, and some guy dressed in a leprechaun outfit, okay, it may not all reach the ground. In fact, it probably won't reach the ground. You'll have a limitation. If it has to travel 5,000 feet through this, heck, that water is going to be chopping the tree down. And that guy's going to be in a world of pain. So relative height does make a difference. And this is where V equals IR come into play, because higher voltage means higher energy. Higher energy means, quite frankly, it means that everything has the ability to break through the impedances a lot easier. We'll talk about this again more in the semester. What you need to know, though, is there is a big difference between I have a small bucket of water and I'm friggin' unleashing the Hoover Dam down this mountain. Okay? There is more energy with more particles traveling down the mountain. If I'm dumping a bucket of water, it's a little bit. If I am unleashing the Hoover Dam, that's a lot. That's flood state. Okay? So the two things that we really have to look at here are the amount of energy per electron and the amount of electrons traveling per time unit. Now, if you know anything about multiplying weird units together, if I multiply the amount of energy per electron, okay, and I multiply that by the amount of electrons, per time, okay, we'll just go ahead and represent these now. So amount of energy per electron, Electrox. It's my new supervillain name. I'm Electrox. It's like a Minotaur, except for with electric powers. Heck yeah, it sounds awesome. I'm gonna quit my job and become a comic book drawer. Oh wait, I can't draw. Okay, so what we have here is amount of energy, so I'll just write it as energy per electron, and then we multiply that by electrons, number of electrons per time. Okay, just looking at these units, energy, this is usually in joules. Electrons, this is usually in coulombs. It's a measure of the number of electrons. Okay, electors. Wow. Electors is Electrox's weakness. Electrons. Okay, and this is in, again, coulombs. Time, this is in seconds. By the way, this is the definition of a volt. And this is the definition of an ampere. Okay? Good. Seconds. Wow. I need to learn how to spell. Or I have the greatest spelling in the world, and it's the dictionary's problem. Okay, so we're going to multiply these two together. You see we have coulombs on bottom, we have coulombs on top here. What we end up with is, if we multiply these together, we end up with joules per second. Which, if you know anything about that, that's power. What? 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 That's what it is. It's a watt. So, we're talking about energy per electron. We're talking about number of electrons. What all of this is combined. These two terms are a way of measuring how much power is actually in your system. Okay? Everything is linked to power. Everything. And this is going to be our next lecture that I'm going to post in like 10 minutes. I want to finish up a little bit of the discussion on voltage and current. Okay? So, to go back to the analogy that I like to use, just to write this out. So here's the analogy. The idea in the analogy is that voltage is like a height difference. Okay, the bigger the height difference, the more energy it has. Current is like a volume of water. The more water you have dumping down something, well, quite frankly, the more energy that's going to have, but the more electrons are moving. You have more water, you have more volume of water. You have more electrons moving, you have more current. Okay, you have a bigger height difference, you have more energy. You have a bigger voltage difference, you have more energy. Okay, and this is really how I like to explain it. Now, I did mention that these are linked through power. We're going to go ahead and jump into a discussion on power. I will be ending this video transmission and moving on to the next link because I think I've beaten this topic to death. FYI, this material is going to show up on the quiz. I'm probably even going to use this analogy on the quiz. So pay attention, take notes, learn this. That's kind of important. Your quiz is going to be a lot of questions on definitions because that's what we're talking about today. Now I'm also going to be posting a reading assignment, which I think I might have already posted, your quiz, a homework assignment, which I also think I posted on Canvas already, and those 3 things today that will be due next week. Okay? All right. I will end this video transmission. I will move on to the next link. So go to Canvas, go to lecture 3. This is the end of lecture 2. So I'll see you in the next video.